I'm here to talk about stuff, and I mean all stuff. The stuff inside of you, the stuff in this room, the stuff on the whole planet. My aim today is to show you that the entire universe can be made out of 20 different pieces of stuff, 20 different ingredients. Now, the story starts back a long, long time ago in a galaxy close to this one, in which the ancients believed that their known universe was made of these four elements: air, water, earth, and fire. Now, that basically corresponds to solid, liquid, gases, and stuff that hurts you when you touch it. That lasted for thousands of years until one day this stony-faced Greek guy woke up with an idea. And he said to himself, what if I take a pair of scissors and a piece of paper and I keep cutting it in half? And I cut and I cut and I cut. Surely there will become a point where I can't cut anymore. My scissors will break. And the Greek word for uncuttable is atomos, and that's where we get the modern-day word atom for. That's the way we get the modern-day atom, which is basically the smallest piece of stuff you can have. Now, if we fast forward a couple of thousand years, two things happened. One is technology advanced, as it continually does, and the second thing is society made a few people so rich that they didn't need to work anymore. And with all this leisure time, they decided they were going to study what was called the natural sciences. So, for example, this guy, John Dalton, he was a chemist. He was playing around with gases and pretty much proved that gases had to be made of atoms and molecules. This guy, unknowing to him, actually invented the TV set. He took a piece of metal, connected it to a battery, a power supply, made it really hot, and noticed that it emitted negative stuff. He didn't know what it was, so he called it cathode rays. This guy had a thought. He thought, okay, if this piece of metal is giving out negative stuff, then the atoms in that stuff must contain negatives. And because metals aren't generally negative, there must be positive stuff in there to balance it. And this caused him to come up with this model for an atom. He thought atoms were cloudy, spherical clouds of positive stuff embedded with electrons. That's what he was calling those negative bits that came off the metal. This guy, Ernest Rutherford, decided he was going to test this theory. So radioactivity had been discovered and alpha particles were being used, and he decided to take those alpha particles and fire at them a sheet of gold metal atoms. He fully expected them all to go through because, after all, the atom was supposed to be mostly cloudy stuff. But to his astonishment, a small percentage bounced off. This is like firing 100 bullets at a piece of paper and seeing 2 of them bounce off. And this caused him to come up with a new model for the atom, which was basically a positive central nucleus. This is what caused a few of them to bounce back. And the rest of it was just empty space with electrons orbiting around, much like the planets going around the sun. Now, he went a little further than that. He then started looking at all the elements in the periodic table, and he looked at their masses and their charges and realized that there must be 2 particles inside the nucleus: protons and neutrons. Protons for the positive charge and neutrons to give it the extra mass that was needed. Now, this was 1920. In 1920, technology was quite good, and it was good enough to be able to prove that the protons existed. After all, protons are just hydrogen atoms. The neutron, not having any charge, was much harder to find. And it took this guy, James Chadwick, to actually build an experiment that was sufficient to find out whether neutron existed. That took 12 years. So in the 1920s, this is what they thought the atom looked like: protons and neutrons in the middle, electrons orbiting around the outside. Now, it doesn't take much to realize that this can't work. Nothing is stopping these electrons spiraling around and hitting the nucleus. After all, plus attracts minus. And this problem was actually helped solved by this guy. Now, this guy, in 1921, was receiving his first Nobel Prize, his only Nobel Prize. And it wasn't for relativity or E equals mc squared and anything he's famous for. It was actually for an innocuous experiment he did in 1905, in which he showed that light, which everybody thought was a wave, actually could be considered a particle. And even more of a head-scratcher, this guy, Louis de Broglie, showed that electrons, which everybody thought were particles, could be made to behave like waves. So this guy, Niels Bohr, Danish guy, took this idea and said, well, if electrons behave like waves, then the waves must fit inside the orbits, and therefore they can't just choose any orbit they want. This stops them spiraling into the nucleus, and now we have a stable atom. This is now what we call quantum mechanics. And the granddaddy of quantum mechanics is this guy, famous for his half-dead cat. Ernst Schrödinger was a mathematician, and he came up with the basic equations of quantum mechanics and showed that the electron is not a wave, but actually a cloud of probability, which is very confusing. So now we have the modern-day atom. Protons and neutrons in the middle, electrons around the outside. This could be considered the end of the story. The whole universe is made of atoms, protons, neutrons, and electrons. But technology was still advancing, and physicists started to build these things. This is a particle accelerator. What it does is it takes charged particles, gives them lots of energy, and fires them down a tube at a target. Back then, they were about the size of a park bench. Now we build them like this. This is the Large Hadron Collider at CERN in Switzerland, and it's so big that it actually goes across the border into France. It's actually two accelerators, two tubes, 27 kilometers long. One takes protons and accelerates them clockwise, and the other takes them and does them anti-clockwise. Okay, it uses so much energy that it uses more electricity than a small city. It is the most complicated machine that man has ever built. It takes those two proton beams and crashes them into each other at these 2 points here. These are two detectors which are literally the size of a 3-story building. They are huge, most complicated things. When you smash things in together with that much energy, two things happen. Things come out. So like if you crash two cars, you see wheels and doors and windows come out. The same when you crash two particles together. The stuff inside the particles comes out, and you can see what's in there. But because of Einstein and his E=mc² equation, the one he didn't get a Nobel Prize for, this tells us that energy and mass are the same thing. So energy can be turned into stuff. So all that energy that we smash these particles into each other with can be turned into stuff. And it turns out that we were using so much energy that loads and loads of stuff was made, so much that we had to call it the particle zoo. And we broke it down into different categories. We have the baryons. Now, the baryons include the protons and neutrons that we know about already, but they also include lambda particles, sigma particles, omega particles, delta particles, and C particles, if I can get this to work. Hello. Anyway, so that's one category of particles. Another category of particles is the leptons, which includes the electron, which we already know about, but there is a big fat electron called the muon, and an even bigger, fatter electron we call the tauon. And these three ghost-like particles which are kind of associated with it. Now, these particles interact with very little. In fact, 100 trillion of them pass through you from the sun every second, which might cause an itch or two occasionally. We have the mesons, which are called pions, eta particles, kaons, and a whole load of other different particles. And finally, we have, coming out of these collisions, force particles. The gluon, which we now know is used to hold protons together in the nucleus because they're both positive charges, so something needs to stick them together. We have photons, which are currently dazzling me here. The W and Z particles, which are used in radioactivity. We have a graviton, which is as yet undiscovered. We haven't confirmed this exists, but we think it does and makes gravity. And finally, somewhat famously from a few years ago, you may have heard of the Higgs boson. That was called the God particle for some reason, and it was discovered at CERN about 6 years ago. Now, this is a gigantic mess. We went from the simplicity of electrons, protons, and neutrons making up atoms to a sudden plethora of particles that we have to call the particle zoo. Now, fortunately, about 60 years ago, some very smart people realized we'd been there before. They realized that in the 1800s, we had all of these elements in the periodic table: lead, gold, silver, platinum, and all these different elements, dozens of them. And at that time, we didn't really understand why until this guy, Mendeleev, looked at all the patterns and properties of these elements and managed to arrange them in a periodic table. He even left gaps because he knew some of them hadn't been discovered yet. And later we find out that all these elements have the properties they do because of the way the electrons are arranged in the atom. That's what we call chemistry. So the question is, can we do this again with all of these particles in the particle zoo? And the answer is yes, we can. We can look at the properties, and we can look at the mesons, for example, the pions, the kaons, and we can arrange them in little hexagonal periodic tables. And the baryons, including the proton and neutron, we can arrange in little triangular periodic tables. And just like every element in here was made of three particles that we know about, we can actually figure out what particles must be making up these mesons and baryons. And we call those particles quarks. Quarks it's a random name that comes from a quote from a book. It turns out there's 6 of them. The proton, for example, is made of 2 ups and a down, and the neutron is made up of 2 downs and an up. And these other ones, the charm, the strange, the top, and the bottom, which is sometimes called beauty, we only see when we smash things together fast enough. The leptons that I talked about, including an electron, don't seem to be made of anything, as we can say for the Higgs particle, the graviton, and all the force particles. They don't seem to have any structure inside them at all. So what we have here is a new picture. The whole universe, we think now, is made of just 18 particles. In fact, everything around you seems to be made of just those 4 particles. Up and down, making protons and neutrons, and the electrons, and those 3 together make atoms. So this is our current picture of the universe. But it's not quite the end of the story, because, again, technology keeps advancing. And when I was at high school, at your age, astronomers were starting to build some really powerful telescopes, and they were looking deep into the universe, and they noticed 2 things. One thing they noticed was that the galaxies are spinning too fast. Now, everybody here has probably been on a merry-go-round, and you go round and round at the fair, and you know that you have to hold on to stay on, otherwise you're going to fly off. Now, what happens if the merry-go-round goes faster is you have to hold on tighter. It's the same for stars. All these stars in this galaxy are holding on using gravity. They're going round and round, and gravity is keeping them in orbit, just like the Earth stays in orbit around the sun because of gravity. Now, the problem is, when you look inside that galaxy and you add up all the material, all the stuff in there, there's not enough to make enough gravity to keep all these stars on the outside from flying off into space. Which means there must be stuff in that galaxy that we can't see. And that's what we call dark matter. Dark, we can't see it. The second thing they noticed was that the galaxies are all moving too fast. Okay, just like if I take a ball and throw it up in the air, you expect that ball to stop and come back down to Earth because of gravity. And you expect all the galaxies, because they're all pulling on each other with gravity, to be slowing down. But it turns out they're not slowing down, they're speeding up. This is like taking a ball and throwing it up in the air and seeing it just zip off into space. So what's the solution there? Well, there must be stuff in deep space, anti-gravity stuff, which is making these galaxies push away from each other. And we call that dark energy. So we can do some calculations if you're smart enough. This is not me. And you can figure out how much dark matter and dark energy is actually in the universe. And it turns out that we need about 1/5 of the universe has got to be dark matter in order to keep the galaxies from flying apart. About 3/4 of the universe has to be dark energy to make the galaxies fly apart like we see them. Which means that less than 5% is the stuff we know about. Everything around us that we know about and can see makes up less than 5% of the universe. Which brings some obvious questions. Brings me to some homework. If you decide you're going to graduate high school and go to university and study physics, and some of you will, and you might join a research group afterwards, these are the questions that we need to figure out. Because at the moment, we literally have no idea. And one of those questions, of course, is what is dark energy and what is dark matter? As I said, people have theories, but at the moment, we have no way of testing them and finding out. Those 18 particles I showed you, why are there 18? What's magic about the number 18? Why not 28 or 58? Are there more? If we get a bigger hadron collider, can we make bigger things? Why do these particles have the charge properties they do? Some of you know that the charge on the electron is 1.6 times 10 to the minus 19 coulombs, but why is it that number? Why not 2.6 or 6.6? And finally, gravity and quantum mechanics, which I mentioned, do not like each other. The theories do not coalesce, and we need to find a quantum theory of gravity. Now, why would we want to do all of this? Well, of course, when we ever get new science, from that comes new technology. That quantum mechanics I talked about led to the microchip, and the microchip has led to virtually every piece of technology we have around us today, from computers to cell phones and onwards. So if we did manage to solve those problems and answer those questions in a couple of decades, maybe we could invent some beaming technology, and we wouldn't have to travel around in our cars anymore. Maybe we could go faster than light and have a warp drive, because at the moment it takes at least 4 years to get to the nearest star. So as far as our galaxy is concerned, we're not going anywhere for quite some time. Maybe we could figure out how to make or discover wormholes. Theoretically they exist, but we don't know how to make them. And if we could go anywhere in the galaxy instantaneously. And maybe we can invent a time machine so we can do all of this yesterday. So, over to you. Thank you.